All right, welcome back, everybody. Today we're going to carry on with our physics lessons. Our physics 11 lesson today is on kinematics, and we are learning about something called the big three formulas in kinematics. So this is kind of a momentous occasion. You might not quite realize the gravity of the situation, but it's kind of a big deal. So whenever we've looked so far at motion, we've talked a little bit about uniform motion, where something's going at a constant velocity, and we've talked a little about accelerated motion, where something might be speeding up, slowing down, so on. But the formulas that we have so far do have limitations. So this formula, v equals d over t, so velocity equals displacement over time, if an object is accelerating, then that's really just going to give us our average velocity. So if you imagine, for example, if something's moving at a constant velocity the whole time, it's going at 10 meters per second, it stays there the whole time, well, this formula works great because the average velocity is the same as its velocity the whole time. But if something starts at 0 meters per second and then constantly speeds up to 20 meters per second, using this formula would tell us that the velocity is the average, which is 10. And that actually doesn't really make sense because it was started at 0 and it ended at 20, and at some point in between it was 10, but that doesn't really describe its motion. So the other way, if you want to find the average velocity, you can also find v average by just combining the final and the initial velocities and then dividing by 2. So that also gives you the average velocity. But what if we want to know a velocity at a point in time? What if we have a rocket ship that's blasting off into space, and I know it starts at 0 meters per second, but I want to know how fast is it going when it's way up in the air? We can't use v equals d over t. So that's where the big three formulas come in. So the big three formulas are the three formulas that are going to use the same 5 variables all the time. And I know at first this is going to be a little bit overwhelming, but I promise you that with practice, you'll be able to master these things. But at first, it might seem a little bit much. So these are the 5 variables right here: v, v naught, a, d, and t. And so v is simply the final velocity. And you decide where the final is. So if you throw a ball off a cliff, maybe the final velocity would be just the split second before it hits the ground. Or maybe it would be at some point while it's in the air. You get to decide that. V naught, this v with a 0 beside it, is going to be your initial velocity. And that 0 literally means at time 0. So what's the velocity at time 0? A is our acceleration. And then d is displacement, not distance. And then, of course, t is time. Now, when you look at those variables, you should think about what they have in common and what they have different. Have a quick scan of those and decide for yourself which of those are vectors and which of those are scalars, okay, when you take a look. Hopefully what you'll notice is that these first 4 are vectors. And so only this last one here, only time. Time is the only scalar. Now what does that mean? That means for any vector, it's going to have a direction, meaning it could be positive or negative. We can have positive or negative velocities, accelerations, displacements. For time, time's always going to be in the positive. So let's get to it. So the 3 formulas are as follows. And I'm going to show you the formulas, and then we're going to do a practice problem with each one. And we are going to practice this more in person because it's going to take a certain amount of practice to get comfortable with it. But the first formula looks like this. It says v final is equal to v naught plus a times t. Now, there is a certain set of strategies that I'm going to insist that we use for all of these problems, and that is going to be the following. We're going to read the problem, we're going to make note of any of the numbers in the problem, and then we're going to go from there. So a squad car, a police car, traveling at 7 meters per second east, speeds up to 22 meters per second east in 1.7 seconds. What is its acceleration? So the potentially useful information that I've identified here, and maybe I'll include the direction in that, are these bits of info. So first things first, we're always going to draw a picture. And if you have done any of my lessons before, you know that I'm a terrible artist. So it doesn't matter how bad you are, draw a picture of this situation first. So a police car speeding up. So, okay, here's my attempt at a police car. Yes. We're going to make it a police car. There you go. Now it's officially a police car. There's no mistaking it. And we know in this initial case here, it was kind of cruising along at 7 meters per second. I'm just going to leave that as +7, and I think of east as being my positive direction. I'll just leave it at that. And then the car speeds up over time. Now he's going real fast. A couple of speed lines there. And maybe he goes so fast the sirens, the lights fall right off. And so now we're going 22 meters per second. Okay, so far so good. Now the next step after we draw our picture is always going to be to write out our variables. And this might seem like a little bit of overkill. Like you might be looking at this problem going, I can already figure out the answer. I can already think of it in my head. Good for you. But the point is that we're going to get to problems that are not as cut and dry as this one. So I'm going to lay out the variables v, v0, a, d, t. And I'm going to identify which of these variables I know. This first number here, 7.0 meters per second, that was the velocity at the beginning of the acceleration, at the start. So that's my initial velocity. So this is 7.0. Speeds up to 22 meters per second, that's where it ended up. And so that's going to be v final. So that's 22 meters per second. Remember that v just means v final at whatever point you choose. And then the last thing I have is time. Time is going to be 1.7 seconds. It's helpful here at this point to just double check. Do any of my vectors need to be negative? I don't think so because we're going to the east, so that's all good. So next step is to decide on a formula. It's pretty obvious which formula to use because it's in the giant box right above this example that you just learned. But in the future, you won't know which of the three formulas to use. So you're going to have to pick and choose. So I'm going to write out my formula. V equals V0 plus AT. I'm going to solve this algebraically first before I put any numbers in. So I'm always going to do the algebra first before numbers. So I want to solve for A. I'm going to subtract V0 from both sides. And so I get V minus V0 equals AT. Then I'm going to divide by t, and I'm going to divide that whole thing by t. And I'm just going to move a to the other side of the equation there, so it says a equals v minus v0 divided by t. Now, finally, after all that, I can put my numbers in. So I've got 22 minus 7 all divided by 1.7. I'm just running out of space here. Now I'm going to put this in my calculator to get the answer. But I just want to point out, if I just punch this in like this, if I just do 22 minus 7 divided by 1.7, that's not going to work because BEDMAS is going to show up, and BEDMAS is going to be like, oh, I'm going to do this division before I do that subtraction. So that will give me the wrong answer. I would need to, and I didn't write it here, but I would need to like include brackets around those terms. So I could do, for example, bracket 22 minus 7, close bracket, and then divide by 1.7. And that'll give me the answer I'm looking for. So 8.824. Last but not least, I'm going to look back at my sig figs, and I see here I've only got 2 sig figs for time, so I'm going to round this off and just call it 8.8, and then include my units meters per second squared. Now, that is a perfectly acceptable answer. I can leave it like that. You might remember that the original direction given was east. So you might say, well, should we say it to the east? By all means, if you want to. I took positive as being to the east, so leaving it as a positive answer implies the direction as well. Either way is fine. Okay, so let's look at another example here. Oh, first, let's get you another formula. You lucky people. Okay, so the next formula is going to start like this. This one's a little more complicated. It looks like this. It says d, displacement, equals v0 times time plus 1/2 acceleration times time squared. So let that sink in for a second. It's a bit of a doozy. First step, a reminder. First step, actually let's go back and look. What was our first step? It was draw a picture. Second step, write out the variables. Third step was to pick your formula, and then finally the last step at the end there was to solve. So I'm going to draw a picture. A sprinter starts at rest and accelerates uniformly. He travels 40 meters in 4.82 seconds. That's pretty impressive that he accelerates uniformly, but let's just pretend that's true. What was his average acceleration? Okay, so I've got a sprinter, just kind of standing here. minding his own business. That's definitely how all sprinters start races. That's exactly what they look like. And then at some later point, running very fast, as you can see. What else do we know? We know that they traveled 40 meters. So maybe I'll just kind of, oops, not 4 meters. Definitely not 4 meters. That's not an impressive sprint. 40 meters. Okay, and they did it in 4.82 seconds. So the interesting numbers that kind of jump out at me, or interesting bits of information, are these two right here. Those seem to be relevant. Okay, so I've got my picture, done. My next step is to write out my variables. And so the same 5 variables all the time. V, V naught, A, D, T. What do we know? Well, 40 meters traveling straight forwards, that means there was a displacement of positive 40 meters. Okay, that's good. Time was 4.82 seconds. 4.82 seconds. Now here's the thing though, I'm looking for the acceleration, right? This is what I don't know. With these formulas, you always have to know at least 3 of the variables. If you know any 3 of the variables, you can always find the missing 2. Just about always. And so I need one more thing. I don't know the final velocity. I don't know how fast they were going at the end. But if you think about it, I do know their initial velocity. Because if they started off at rest, well then their initial velocity was 0. They weren't going anywhere. And so because now I've got 3 variables, this is going to work. I'm going to write out my equation. D equals V naught T plus 1/2 AT squared. Now, I know I just finished telling you to always do the algebra first and then put the numbers in. And it turns out that was a small lie, because there's one time when you can put a number in right off the hop, and that is when it's a number that will make your life easier immediately. It'll make the whole algebra easier. And that number often is this number right here, 0. If something is 0, go ahead and put it into your formula and see what's going to happen. Like, what happens if I put a 0 in here for initial velocity? If the initial velocity is 0, it doesn't matter what the time is. 0 times anything is going to be 0. And so this whole term here is going to disappear. And what's nice about that is it then means that this equation becomes D equals 1/2 AT squared. And that's going to be a little bit easier for me to solve algebraically. So I just did myself a favor. So I'm solving for A. So first thing I'm going to do is I'm going to multiply both sides by 2 and to get rid of the 1/2. And so I end up with 2D equals AT squared. And then I'm going to divide by T squared, and these cancel out. That's gone with that. And I'm left with A equals 2D over T squared. Now I can put in my numbers. So 2 times 40 divided by 4.82. And don't forget the squared. It's so easy to do all that work and forget that little squared at the end. So when I put that into my calculator, again, just be careful with brackets and things. So I can, in this case, I can just do 2 times 40 and then divide that by 4.82 and then hit the squared button. And that will be just fine. There's no bed mass problems that are going to arise. This will get squared first and then it'll get divided in due time, so it's all good. When I hit enter, I get 3.443. which looks like 3 sig figs for this one. I'm going to call it 3.44 and then meters per second squared. And again, acceleration is a vector, but the direction is implied by the fact that it's positive. They were accelerating forwards in the positive direction. All right, last but not least, everybody's favorite, number 3. The third formula looks like this. It says V squared, V final squared, equals V initial squared plus 2AD. All right. And let's read through this problem and see what we can find. Banana boat, whatever that is, accelerates at 15 kilometers an hour at 2 meters per second squared. How far has it traveled when it reaches 30 kilometers an hour? So those are the important bits of information. I might also just kind of highlight this right here. How far? Because that kind of tells me, that's a hint as to what the question is. that we're trying to answer in the first place. Okay, so first step, draw a picture. I've got a banana boat accelerating. So I'm going to assume that a banana boat looks like a banana. Don't actually know. And then it starts at a certain speed. And then it speeds up. So it's going faster. Now, what do we know? You know, here it's cruising along at 15 kilometers per hour. And then later on it's cruising along at 30 kilometers per hour. Okay. So it's accelerating. I'm going to write out my variables, v, v naught, a, d, t. I'm going to write out what I know. Let's see. Accelerates from 15 to 30. So the initial velocity is 15 kilometers per hour. And the final velocity is 30 kilometers per hour with an acceleration of 2.00 meters per second squared. Now, that's all good. Oh, I should point out too, the question we're looking for is how far. So what we want to know is the displacement. What was the displacement this time? It's really tempting to just go launching in with our equation, but it's a good reminder at this point to just kind of, this is why it's nice to set up your variables like this. These variables are all going to be positive, the vectors I mean, because we're going forward and we're speeding up forward, that's fine. But something's wrong with them. We can't use kilometers per hour. That's not our base unit. We have to put that in base units, which is meters per second. Now a reminder that the shortcut to going from kilometers an hour to meters per second is to simply divide by 3.6. So I'm going to divide both those numbers by 3.6 to get my my velocities in meters per second. So 30, I don't need to put 0.00. Divide by 3.6. 8.33333. So 8.333. The original number had 3 sig figs. I'm going to keep one extra digit, 1 or 2 extras as I do my calculations because I don't want to throw off my answer just by doing some sort of rounding error. 15 divided by 3.6 is going to be 4.1666. So 4.167, let's say. And that's now in meters per second. Okay, so again, I've drawn my picture, I've got my variables, I'm now going to choose my formula, which again is easy because it's right there, but in the future it'll be more challenging. V squared equals V naught squared plus 2AD. And what are we solving for? Well, we're solving for displacement, that's what we want to figure out. So, SAMDEB. SAMDEB says let's get rid of this, V naught squared. Let's cancel that out first. And so I get v squared minus v naught squared equals 2AD. And now let's divide by 2A and divide this whole thing by 2A. The 2 cancels, the A cancels, and I'm left with D equals v squared minus v naught squared divided by 2A. So I'll put in my variables, put in my values, 8.333 squared minus 4.167 squared. Divide that by 2 times 2.00. Now, we can put this in our calculator. We can do this all in one go. And you definitely can do it as long as you're really careful with your brackets. I'm going to suggest, though, that as these get more and more complicated, it might be simpler for you to just break it out into chunks. So, for example, when I've got a fraction, a rational, I might just look at the numerator and then divide it by the denominator, and that might simplify things for me. So I'm just going to do the numerator first. So 8.333, I'm going to square that, I'm going to subtract 4.167 7 squared. I'm just going to hit enter. So now I know that's what the top equals. I'm now going to divide it by, and here's why I have to be careful with brackets, 2 times 2.00, and then I get my answer, which is, so I get 13.02. 13.02, which rounds off to 13.0, and I was looking for displacement, so the units are meters. And that's my final answer. Okay, so as I said, this is really just an introduction. We're going to have to do a lot of practice with this stuff, and we will do that in the coming times. But that is it for the big 3.